Welcome to Spirit of Math, the channel devoted to mathematical curiosities. In today's video, we will explore the nature of A, the Euler's constant. Euler constant, A, which is approximately equal to 2.718, is one of the most important constants in mathematics, like pi or a, and it appears in many areas of mathematics, analysis, probability, number theory, and so on. It has many definitions. It can be defined as a limit, a equal the limit of 1 plus 1 over n power n, or it can be defined as an infinite series, the famous infinite series, the sum from 0 to infinity, the 1 over factorial n. The nature of A has fascinated mathematicians since the beginning, and in 1737, Euler gave a proof that A is irrational. This means that A cannot be written as the quotient of two integers. In 1873, Charles Hermite, a French mathematician, went further and showed that A is transcendental. This means that A cannot be a solution of a polynomial with rational, with integer coefficient. And recently, in 1947, Niven gave an elegant proof of the fact that A power r, where r is rational, is also irrational. This proof, in the same paper, Evans proved also that pi and pi square are also irrational by the same method. In a previous video, I gave Evans' proof of the irrationality of pi square. So today we will see the first rigorous proof of the irrationality of A given by Charles Hermite, and I will give Evans' proof of the fact that A power r is irrational. So let's go. The Hermite proof of the irrationality of A. This is a proof by contradiction. So we suppose that A is equal A over B, and we choose an integer such that B over n is strictly less than 1. Such integer exists because this sequence B over n goes to 0. And the trick, if you want, we remark that if we multiply B factorial n by A is equal A over B, we get A factorial n which is an integer. Now we will show that actually this quantity cannot be an integer, and we get a contradiction. So we write B factorial n E as alpha n plus beta n by using this expression. So we alpha n is the we choose the first term until 1 over factorial n, and here, because we have here factorial n, all this quantity is an integer, because we will get 1 factorial n here, multiply factorial n is 1 over factorial n minus 1 is equal to n, and so on. So we get that alpha n is an integer. Now for beta n we simplify, because we start here at 1 over n plus 1 factorial, we multiply by factorial n, and we get this quantity. Now we will show that beta n cannot be an integer, and we get a contradiction. And to do so, we remark that this term, of course, is less or equal to 1 over n plus 1. This term is strictly less than 1 over n plus 1 square, because n plus 2 is bigger than n plus 1, and the inverse is less, and so on. So what we have shown here is that, of course, beta n is positive, and this quantity is less or equal to this geometric series. And we have the formula for this geometric series sum from k equal to 0 to infinity, the k power n is equal to 1 over 1 minus k. So we get this, because here we start at 1, so we must subtract 1 here, and if you compute this, you get 1 over n. So we have found that beta n is less than b over n, and b over n is less than 1, and so beta n cannot be an integer, and we get the contradiction. And we have done. Let's tackle Niven's proof of the irrationality of a power s over t. First, we remark that a power s over t power t is equal to a power s, and to prove that a power s over t is irrational, it suffices to prove that a power s is irrational. So we will show that a power s is irrational when s is an integer. The proof, as usual, is also by contradiction. We suppose that a power s is equal a over b, and Niven consider this polynomial sequences fnx equal x power n1 minus x power n over factorial n, and he consider this integral n capital N equal to bs power 2n plus 1, the integral between 0 and 1 a sx fnx dx. And what he showed that this integer is positive, this quantity is positive, it is an integer, and the limit is equal to 0. And now here we get the contradiction, because if you have a sequence of integer which converges to L, then it must be constant, because the integer has between un and un plus 1, there is at least a distance of 1, so it cannot be converge vers L unless it is constant. So now we have the contradiction. We have the contradiction. Now we have three parts. We have the most difficult part is to show that n is an integer, and we will give it at the end of the proof. But this property and this one is easy to prove. For this one, we have here n is an integral of a continuous positive function. So the integral of a continuous positive function vanish if the function is equal to 0 for any x. So this integral cannot be equal to 0. Now to show that this limit is equal to gets to 0, we remark that f nx is less or equal to 1 over factorial n for x in the interval 0, 1, and hence this integral is less or equal to a s power 2n plus 1 over n, because b because a sx is less or equal to s, and it suffices to prove that this limit is equal to 0. So it's what we will do. So first we will show that this quantity is positive, this limit equal to 0, and at the end we will show that this integral is actually an integer. So let's start by proving these two results. First, we have this classical result in analysis. If you have a continuous function on an interval and its integral is equal to 0, so the function must be 0 for any x in the interval. So now we have that our function is positive, and it doesn't vanish, so this integral is non-zero. And we have also that n is this integral is less or equal a s power 2n plus 1 over factorial n. And here we have n is strictly positive. Now we will show that this sequence converge to 0 to get this result. It's easy. We use the Stirling formula for factorial n. We have this noun formula for factorial n, and we get that the limit of un is equal to the limit of this quantity, and this quantity, by using the exponential expression of the power n, we get that this quantity is equal exponential n ln s square a minus ln. This goes to infinity plus infinity, this goes to minus infinity, so this quantity goes to minus infinity, and exponential of minus infinity goes to 0, and we have shown that limit of un is equal to 0, and then the limit of capital N is equal to 0. Now we tackle the most difficult part, is to show that this integral is an integer. And In fact, it is the mysterious part of the proof of Niven's and the tricky part of its proof, because Niven's found an antiderivative of this function, and which give them the fact that, so here since fn is a polynomial, so we can use integration per part, but it's not clear, because we have some constant with a pairs, but Niven's found an antiderivative of this function in my opinion, by a mysterious way. So let's give the proof of Niven of this fact. So first, we consider this polynomial function. It's a polynomial of degree 2n. It can be written as 1 over factorial n, and a polynomial where the ck are integer. It's clear that it's fnx is positive and less than 1 factorial n, and the most important property of this polynomial, that all its derivative in 0 and 1 are actually integer, and they think that it's the reason why Niven's introduced this polynomial to get this property. So let's show this. This can be shown easily, because if you compute the derivative of n at 0, you get 0, because this polynomial starts at xn. So we get 0 when k is not in the interval n to n, and you get factorial k ck over factorial n when k is between n and 2n, and factorial k over factorial n, since k is bigger than n, is an integer, and we get this for fn k to 0 in n. For this one can remark a symmetry of this polynomial, namely that fnx is equal fn1 minus x, and so we get that fn power k1 is equal minus 1 power k fn k0, and we have down. So we have this important property of this polynomial. And now Niven considered this function, and the important property of this function, that f1 and f0, capital F1, capital F0, is an integer. It can be negative because we have this minus here. And we use the fact that f and k in 0 and 1 are integer. So we differentiate this function f prime x. So it's we derive this quantity. We replace k plus 1 by k. And we get this formula here. We replace by k minus 1, and here we start at 0 to 2n, so we start here to 1 to 2n plus 1. And we factor by s here and by minus 1 here. And here it's look like the definition of f, only we have not the term k equal to 0, and we have the term k equal to n plus 1. But this polynomial fn is of degree 2n, so this polynomial is equal to 0, so we get here that this quantity equal s minus s fx, and we add the term k equal to 0 to get what we want. So we have now that the derivative of x is equal, and as you can see, we are not far from the antiderivative of exponential s x f n x. And now we have this formula, and now we give the antiderivative of our function. So we consider this function, we differentiate to get this quantity, we replace this derivative by this relation, and we get that this term and this term will cancel, and we get what we want. So g prime x is the g the x is the antiderivative of our function. Now we can compute n capital N by using this formula, and we get the fundamental theorem of calculus give us that this is b g1 minus g0, and if you compute g1 and g0, they are equal to a f1, which is integer, and minus b f0, which is integer, and we have down. So now we have that n is an integer, and this completes the proof of Niven theorem. Okay, so to support the channel, please like, subscribe, and share. And thank you.